All right, so here we go. This is one of the animations that you see, and in the instructions that I put in your reading. So reading this textbook might be something that you'll need to do a little bit differently from how you read, paper textbooks, look through, see some stuff. That's great. This one has a lot of moving parts, and it's important that you pay attention to the moving parts. They were done deliberately so that you can take some time in and see what happens. Instead of you having to, maybe like in a paper textbook, they say, now grab a graphing calculator and do this and see what happens to it. What we're trying to do with this is, it's right in the middle of your textbook. So you're reading, and then there's something you can just look and see what happens. So in this, at the beginning, it says dy equals mdx. We talked about that relationship in class on Monday. But you can see at the beginning of this, there's x and dx both on the bottom. And I've got a b and mdx written on the top. And as I let this animation progress, or you can even kind of, just scoot it along manually, the red bar on the bottom grows a little bit longer. The x and the dx, they suddenly aren't on top of one another anymore. And you can see there's these little gray lines separating this. So little gray lines segmenting, all right, here's a little bit of x that corresponds to a little bit of this blue bar up here. So there's x's and dx's, so I called this x. And here's some other x-ish stuff. And that corresponds to the next chunk of this blue bar. And if we let this go, now the x and the dx on the bottom are getting farther apart. What do you think the x in this diagram, like there's an x symbol there, what is it representing, or what part of that picture do you think means to correspond to x? Any thoughts? Is it the green part? Is the green part x? No. The green part clearly labeled b, and it's not moving. This x thing is moving. So is dx. So so what was that?
Time.
Okay, so we could think of it as time. And in fact, when we push this, we see as time goes on, we've got, well, x and dx are both moving. So maybe x is something, we could think of it in a context as something about being time. Yeah?
X would be representing the entire red bar.
Okay, so x may be represented by this entire red bar, so its length varies. It started at nothing, and it's getting longer as time goes on. So if we wanted to make this something about, okay, x is time in seconds since I started the video, which it will be at least at first until we restart it midway through the video. But yeah, at the beginning, I have x representing time as 0, and it gets longer and longer and longer. So what on earth is dx then? Yeah, so dx, we talked about the symbols dy and dx, or dx and dz. We represented those as a change in or a variation in x or z or whatever the underlying variable is. So if I say x is the amount of time since I started the video, then this dx here, which is always hanging out by the end of this red bar, as this goes on, x kind of is in the middle, so I think, okay, x represents the entire length of it. Then this dx is just these little incremental changes. Now we can let it doesn't have to pop up one chunk at a time. We can still let x vary smoothly, and I think you saw that in one of the other animations here. Let's let x vary smoothly from time 0 up through time wherever I stop it, 8 seconds so far. But this dx is a little tiny thing that's at the end. So it looks like we're considering small changes in x at a time and mapping those to, well, how much does the blue bar change? Every time I change x by small amounts, or as I let x vary through a little tiny gray delineated interval. There's no hash marks on this, to say, okay, this is 1, 2, 3, etc. But if I go a little bit forward, let's see if I can, I was trying to get one more little gray bar. If I go a little bit forward, I get a little more length to the red bar at the bottom, corresponding to a little more length to the blue bar at top. So if x is the entire length of the red bar, and we talked about these dx's being changes in, we can think of this dx as representing just this little, and we have to divide it up into something so we can talk about it, but these little tiny, maybe it's one, like half of a second, something like that, but as x goes through half a second at a time, every time it goes through an additional half second. If I have this dy equals mdx, changes in one thing are a constant multiple of changes in another thing. In this case, maybe the change in the length of the blue bar is a multiple of the amount of time that's passed. Well, every time x increases through half a second at a time, y increases through the same multiple of m, if you can see at the top. And by the way, this whole animation was made in GC. It's kind of a complex one to make, but that m at the top is 1.6. So that's our constant multiple that's being used right now in the animation. If you saw the whole thing before class or looked at it between Monday and today, you saw that during the course of this video, that slider is used and it's changed to different numbers. But right now, if I change x through half a second, while x is changing through that half second, the blue bar is increasing by 1.6 times that half second. So whatever that is, 0.8 in length. You could make whatever story you want to go with this. There wasn't a context with this at first. There's something about Stan and something later on. But in any case, yeah, the dx is talking about these small incremental changes that still happen smoothly. Goes like through each of these little gray intervals as we let x go across smoothly. We can think about small changes occurring smoothly also. They don't have to stop and restart or come in chunks. But every time I make a small change in x, there's a corresponding small change in y. Or if I look at just a microscopic version of this, if I let watch x change just a little tiny bit, I'm going to see y change just a little tiny bit as well. And it changes 1.6 times as much, whatever the units on this might be, whether it's miles that y ends up changing by because of 1.6 miles per hour, and this is hours, or whatever this might be. But if we look at this, we've got x changing and y changing. But these dx and dy, what we're doing is measuring the corresponding sizes of change between them. There's a proportionality that stays the same throughout. Right now it's this proportion of 1.6. The ratio of the changes, y to x, is 1.6 to 1, if you want to think of it that way. Sometimes it said y with respect to x when we're talking about a rate, as opposed to if you're talking about standard ratios. Ratio of win to losses is 3 to 1. If we're talking about this rate of change between y and x, lots of times we say this rate of change happens at a rate y varies at a rate 1.6 with respect to x. It just means 1.6 times as much as x varies. But again, 1.6 was arbitrarily chosen. If we move it to something else, we can see that this, now with m equals 0.4, the length y, or that m dx. So is y the same as mdx? First of all, are those the same or different? Y and mdx. They're different, right? MDX is this little tiny incremental change in the blue bar. Well, it could be bigger, like it is right now. But it's that MDX is the incremental changes or the incremental variation of this blue part on the top. So on the bottom, there's an X labeled, and the full length of the red bar we decided was X. What do you think would be a corresponding value of Y? How would that be represented by what's up top?
Green and blue.
Yeah, the green and the blue combined. That would be like, so Y started from a value of B at some point in time, but it had a value of B, and then it kept getting bigger. If I want to call this X and Y, the incremental changes in Y are the little tiny sections or the little incremental variations in length of the blue line, but the full value starts at the beginning. So it starts at, so the whole top line. Right now, the value of X is, I don't know, I don't want to say it's 58 seconds because we've changed this a lot, but let's say this is, 7 seconds or something to get here. Well, the whole value of what? This is 0 to 7, where the last little dx that got caught on there just happens to be the last little variation or the last little interval of numbers that x went through. And then The y value, though, is all the correspondences. The changes in y, there's an overall amount of change in y since the beginning, which would be the blue, but it didn't start from 0. And you've seen a lot of situations like that. Like, things don't have to start at 0 and change from there. Lots of times, if you have a time element, you will say, okay, I'm going to start measuring now. So the beginning is time 0, but whatever it is you're measuring doesn't have to start at a value of 0, whether it's $0, 0 miles. You don't have to start from everything 0. So that's why just this diagram here, we have this mystery number b, which the letter b was chosen for possibly obvious reasons from notation you've used before in algebra classes. But in any case, the value of y is the value of all of that. It's not b plus m dx, it's the length of the green segment and the length of the blue segment. And the blue segment is all of the different mdx's appended together, right? Because there's a whole bunch of those little small variations that we have one after the next after the next. All right, so let's get back to, a couple things before I start with anything else. You've got, if you want to work on an extra credit assignment coming up due soon on iMath AS. There was one problem that was scoring things wrong that I know about from previous days. Somebody else mentioned something that I'm going to take a look. There are some kind of rounding issues where GC is rounding and you were not, so your answer is actually better. Don't worry, I'll take care of looking through those. Let's see. Oh, also on iMath AS, I did post more assignments than stuff we've talked about so far. So homework 2 is due Monday night. I'll see you a couple times before then. So we still got some material to talk about relative to that, but I just thought I'd post it early if you want to take a look. And when you do go into the assignments, remember it'll show you what section in the book it pertains to, and there's links back from every question to where this is discussed in your text. So make sure you use those, look at the animations that are around there, etc. But a lot of this we haven't talked about or been assigned yet. I just posted stuff early. Yeah.
If you, like, say, answer the question correctly on the 4th attempt compared to the 1, is there any differences?
The 4th attempt, yes. So the first 3, you get the same value. If it after 3 attempts, it deducts 10% per additional attempt. You'll just see that it's not very much. Like the homework, all of your online homework put together is less than 15% of your grade because there's other things in the homework category that aren't iMath AS. But yeah, so all of them put together. So don't worry about a few little tenths of or 10% here and there per question. But if you are having trouble understanding what it's asking for, especially if it's something we haven't discussed in class yet, maybe wait a little bit before you try it again. I think it tells you someplace or another about the 10% at the beginning of the assignment when you first open it. But yeah, the first 3 attempts are the same. If you take 4 or 5 attempts, then it does deduct 10% each for each of those from that individual question. Homework 3 I also posted. That's not due for a while. So homework 2, we're going to finish up talking about that material between today and Friday. And homework 3, we haven't really talked about that stuff yet, but I put it up early in case you wanted to either take a look at it or investigate trying some of the questions early. But just so that it's there in advance, these are the remaining assignments that you'll have prior to the first test that are in iMath AS. All right, so let's see. We were talking about constant rates of change. So do I have this on? Make sure everything's going to work properly. Let's hope. All right, so here's where we were kind of talking about this relationship between changes in one variable with respect to changes in another, where we have a constant rate of change relationship, where a small change in one always gets multiplied by the same constant factor to indicate how much change there is in a second variable. So we talked about a couple things like miles per hour, 70 miles per hour example, and something about $2 per gallon example back on Monday. So here's a different example. I put in a B to match the animation we were just talking about. Store sells make your own snack mix gifts. So I didn't want to write a whole paragraph up here, but this is the kind of place where you pick out a pretty box to put it in. You have to pay for the box. You put in whatever snack mix or candies or whatever you want inside that costs a certain amount per pound in this case. We've got $2.75 per pound. And so thinking about that rate, the $2.75 per pound. If you remember what we were talking about on Monday, how could I explain what that $2.75 per pound means in a general sense? Like in the most general way we can talk about using this $2.75 per pound. If you want to start with a simple example, that can maybe help you modify that or improve it to a more full definition. But if the snack mix costs $2.75 a pound, maybe the easiest definition is if you add a pound of snack mix, your box is going to cost $2.75 more than it did before, right? How could I make that a better definition that covers more cases? Yeah.
It would be the rate.
Okay, so $2.75 is the rate. So how can I precisely define how to use that rate? Not just if I buy one more pound, then it costs me $2.75 more than before, but yeah.
For every additional pound of snack mix purchased, the total price increases by $2.75.
Okay, so for every additional pound, my cost increases by $2.75. So that would cover if I buy 1 pound, 2 pounds, 3 pounds, 4 pounds. Can you make that more general?
For any incremental change in snack mix, your price changes at a rate of 2.75 times that change.
Okay, that sounds good. So don't be afraid to use the word pounds in there because, yeah, I know you don't want to say like necessarily just per pound, but for any incremental change, you said, in the amount of snack mix bought, you can say measured in pounds. That way we know what the units are, but you're not kind of implying to people that it has to be a whole pound at a time. Yeah, so for any incremental change in the amount of snack mix bought, measured in pounds, what was the rest of it?
Your price is that change times 2.75.
Right. The change in the price would be that amount times 275, and the price change would be in dollars, which lots of times people kind of infer when they're just talking in this country because all of our prices are in dollars. But yeah, to be precise about it, there's a lot of different ways you can word it. There's not just one magical way to word it. But when you're trying to word these things, and we're pressing on this for a reason, it's very important not to just indicate that we're talking about you have to change by a full unit at a time, because we want to be able to change incrementally by any size and know what the relationship is. There is a pretty cool animation up above on the page, the one that I was showing earlier, that talks about, it starts with kind of a graph that you maybe made in algebra looking thing. There's like a bunch of dots in a row, and you think, all right, so I connect the dots. But there's lots of other ways those dots could be connected if you don't define your constant rate thoroughly enough. So take a look at that animation if you haven't. But yeah, for any incremental change or any small change or any amount of change, there's a lot of different this, or any variation in the weight of the candy that you're putting into the box, we measure that change or variation or extra in pounds. Take that number times 2.75 and you get your incremental variation in dollars of the price of the box. So what about the B? Do I have to like multiply B by 2.75? No, that's just there. That's like the green bar in our last animation, right? That's kind of a starting point. If you bought some box, whatever price of box you bought, there's probably a variety of different fanciness of boxes that cost different amounts. Whatever price that is, we start from there and then incrementally increase the price of your gift box by $2.75 per pound at a time. But you don't have to put in a whole pound for the price to change. And it doesn't suddenly jump with any little tiny bit of a pound. However much that variation is in the weight, measured in pounds, the price will vary by 2.75 times that amount in dollars. So again, lots of different ways to word it. And when you're trying to do these sorts of things, you'll see some questions like this in iMath AS where it's an essay question, like there's a box and it asks you to explain. Think about maybe first the easiest way you can interpret that to make sure you have kind of set in your mind, and then refine that so that it will expand it, I guess, so that it covers more cases than just 1 pound or integer number of pounds or whatever the units are that you get to change on your own. But all right, let's take a look at defining some variables for a particular problem then. So if I say that X is the number of pounds of mix in this gift box, like so I'm buying a gift and I've put in X pounds of mix, what would the meaning of Y be if Y is the other variable in this relation? Like I've got dy equals mdx. If I've defined this X here, I know kind of what Y has to be. How could we define what Y is? Yeah, so Y would be, what would be the price? Total price, including the B. It just total from the beginning to the end. So like the green and the blue chunks put together, wherever that goes to, that's our Y. So the cost of a gift, I'll say with X pounds of mix in it, just to relate it to the other one. So we're going to talk about this more in depth next class. But when we have this relationship between two quantities that are changing, we usually think of one as the independent variable in the situation. We're going to talk about what the word variable means, which seems silly, but variables vary. We talk about one as independent, or you get to control that, or maybe one we think of first, and then the other one depends on that. So in this case, I'm saying, well, you get to pick how much snack mix you get, and then the price is just, well, you calculate it based on that. It's not your choice what the price is. You could choose a price and then carefully weigh out how much candy to make that price. But the way we're formatting this is like, okay, if I say X is this amount, then Y depends on the total price. I don't know what B is, and I don't know how many pounds of snack mix I have, but I could find it if I knew what X and B were. So if X is the number of pounds of mix in the gift, dx, it represents we're changing that number of pounds of mix in the gift. So there's a lot of different ways you could phrase this, but it's not just the total number of pounds or the current number of pounds as you're putting it together. It's a change that you've made, so from one thing to another. So if you remember from the gigabytes of memory or something, it was the X final minus X initial. We'll have Z in that example, but final minus initial, that's that small change. Now, we don't actually have to have a small change for this to be valid since it is a constant rate of change. We'll imagine small changes at a time regardless. So dx is a small change in the weight of the gift. So what would dy be then? Yeah, a change in the cost that corresponds to that. Or I can think about X varying, and as I dump a little bit more snack mix into the box, as I let X change by a little bit, or as I let X vary by a small amount, then the price will vary too. Now, I'm not going to ask the person every single time I put one more peanut into my snack mix box, what's the price now? We'll figure it out when we're done. But dy can be the small change in cost, where dy equals mdx, and what's our value of m? 275. The units on it are dollars per pound, and that's representing this constant rate of change, the rate from y to x, or the rate more often says y with respect to x. That's a lot of words. But the constant rate of change, it's 275. I put the dollars per pound at the end. That's maybe not standard way you write it in an English sentence, but the units I tried to put at the end on these. So we've got pounds, dollars, and dollars per pound. So make sure when you're defining variables, notice what these kind of have in common. There's a description, not just X is pounds or X is snack mix. I need to say that X would represent the number of pounds of snack mix in the box. And Y isn't just cost, or Y isn't just cost of a box. It's Y is the cost of the gift with the snack mix in it, and it's measured in dollars. Now, measured in dollars is sometimes, I said, just kind of implied, but we should be specific. So when you're defining these variables, these quantities that change, or m, which isn't changing, so it's not called a variable, so that's why I just have these symbols. M is a symbol that's representing a constant rate here. So I'll call m a parameter. Parameters are values that are constant within a particular situation, so it's not changing during this problem. But at a different store, or if I'm buying a different bin worth of snack mix, maybe there's the fancy mix and the regular mix, maybe it's a different rate in dollars per pound for the chocolate-covered stuff, whereas this is just the mixed nuts and fruit cost. So we'll talk about these definitions. I don't think we'll get to them today. We'll see. But Friday, for sure, we'll talk about the difference between a variable, which x, y, dx, and dy are all called variables. They change throughout this problem. dx's and dy's just change by little bits until we start over. You can imagine them changing a little tiny bit, then the next little tiny bit, and the next little tiny bit. They grow and then start over every time we get to the end of one of those gray banded intervals. You can imagine them as small as you want. But x is just this total value as it accumulates, and y, the total cost in this case, as it accumulates due to putting in more snack mix. But in any case, m isn't changing here, so it's kind of a different thing than that 4 above it. It's a constant value, but we have a symbol for it. So we call this m a parameter rather than a variable, because we just have chosen a value for it and we're going to use it throughout this problem. But we could choose a different value for it for a slightly different situation that may be at the same store. It's not a universal constant like pi. So I don't want to say that m is a constant. M has one constant value, but it could be different for something else. It's not a magical number that everybody knows 275. All right, so let's think about those variables and this situation. So you put some snack mix into the box, you look at it like, no, I want a little more. So the additional cost you'll pay for 1.5 pounds more of this trail mix, snack mix, whatever it is supposedly 2.75 times $1.5. So in this scenario, what are the values for these three symbols? The values of the first two variables and the value of our parameter m. Let's see, what's the value of dx in this situation? 1.5. And you can even think of it as a positive 1.5. Remember we talked about these changes can be positive or negative. Even if the overall weight is never going to be something negative, I can increase or decrease weight. So we're increasing by 1.5 pounds, so dx would be our 1.5. Let's see if I can get this to work, and I'll write this on here. Sorry. Touchy today. All right. So if dx is, that's a little big. So if dx is this 1.5, it's the additional pounds. Of snack mix, trail mix, whatever kind of mix you want it to be. So it's this 1.5 additional pounds of snack mix that we've put in there. dy? Yeah, it's this 2.7. So you could think of it, oh, well, dy is m dx. So in that case, that means it's our, let's see, m is the same value throughout this problem, 2.75, and it's dollars per pound. But m dx then, meaning the same as dy. So you can replace one of these symbols with the other. So I can replace the symbol dy with the combination of symbols or the product m dx. Those mean the same thing if I've got a constant rate of change relationship. So some of this may seem like, oh yeah, I know that. But then you're like, oh, you can replace one with the other because they mean the same thing, or we're saying that these are equal because we have a constant rate of change relationship. So this would be that 2.75 times 1.5. Or we could work out what that is, $4 and something. 412? All right, so yeah, $4.125, and we'll figure out if you want to buy any other stuff before we do any rounding. But this would be specifically, if you multiply those together, you get that. But this expression gives us a value of dy in this described situation, or this expression tells us what dy means. But yeah, if I wanted to give a value for dx based on the situation described, it'd be this 1.5 pounds. Question?
Don't you also have to account for the cost of the box?
Oh, so yeah, what about the cost of the box? Right, yeah. So if you remember in terms of the red and blue and green stuff on that first animation today, the value of y would be the total cost of the box, or the total cost of the box of mix, including the cost of the box and the cost of the mix at $2.75 per pound. But yeah, this dy is just an incremental change. So if I knew the cost of the box was $30 so far, and then I added in 1.5 additional pounds of snack mix, do I need to know the cost of the box to find this? No, it's just that this is just the extra cost from the extra snack mix. So it's how much the cost changes as you dump in that extra 1.5 pounds of mix. Yeah, so make sure we keep these, they're all related, but y and dy is a little piece of y, and dy is related to mdx, or the change in the cost as you pour in more snack mix is related to the weight of the snack mix. Unless you're putting more boxes under it, you're not going to have to worry about what b is. So if it required another box because you got too much, then we'd have to worry about what the cost of the box is. But if we're just incrementally adding snack mix and dealing with that, assuming that we don't need more boxes, our cost is just a multiple of that number of pounds of snack mix as we pour it in. All right, questions on this one? All right, let's take a look at another one. Let me clear all this off, actually. Maybe. Come on. All right. Sorry. All right, so we did this. Now, same snack mix box, etc. Don't have to worry about how much there is in it right now. Did I put that 1.5 pounds in or did I not? That shouldn't really affect your answer to this. But think about the values that we could write for the expressions. In this case, you remove 0.4 pounds of snack mix from your bag or box and return it to the bin. So what is dx here? Yeah, the dx is negative 0.4. dx and dy can be positive or negative. It doesn't indicate that you've broken the laws of physics and you have negative mass or weight or anything like that, or negative time if that were an element. It's just a change, so things can go increase or decrease. And so we've got negative 0.4, the negative indicating that we're removing this 0.4 pounds. The units on this are pounds, and that, look, if you don't know what's going on here, I can't have negative 0.4 pounds of something. Remember, this isn't how much I have, this is how much we're changing the weight of the box by. So you can change a weight by negative 0.4 pounds, and that's perfectly legal. What about dy? Aside from being mdx, it'd be, negative 0.4 times our, 2.75, which would be a negative result. Something about dollars, because since y is in dollars, dy is in dollars. How much is this, by the way? Negative 1.1? Okay. So I'll put 2 decimal places since it's dollars, just to make it seem kind of sensible. But what is this negative $1.10? Is this you go up to the register and they hand you $1.10? No, only if you already had paid for your snack mix and you're like, wait, I don't quite want this much, dump this back, and you've given them cash and they say, okay, that's $1.10 less, they give it back to you. But this is just a decrease in the total cost. So you're not paying negative dollars, you're decreasing the cost by that. So there's working out the value is one thing, and then understanding what that value means depends on understanding what these variables are about. So dx is a change in something, dy is a change or a variation in something, or an incremental adjustment in something. So I'm decreasing my weight by 0.4 pounds, and therefore the cost decreases by $1.10. So make sure you can calculate the values, but also make sure you know what they mean. All right, so M is still 275 as it was before. All right, let me clean this up, and maybe, there we go. All right, different example. So I'm jumping straight to the full definition on this one, but if I have a soldier lowering an American flag from the top of a pole at 0.75 meters per second, ceremonial sort of, something's going on, maybe a trumpet playing, during any interval of elapsed time, so as time goes by any small amount, the flag is going to become lower, and it will decrease in height above the ground at a rate of 0.75 times however much time has gone by. So for any increment of time, we'd want to measure the time in seconds, so that we could take that number and multiply it by negative 0.75 and do something with that. Have a result in meters. So if I have elapsed time in seconds, the height of the flag decreases by 0.75 times that number of seconds, however many full or partial seconds that is. Because it's a constant rate of change, but we'll imagine small bits at a time, just in case wind kicks up and the cord ties in a knot. And maybe it's not constant all the time. But take a minute and see if you can define these, well, I'll say 4 variables in a parameter, completely, precisely. Think about what it is that's being measured and what units you measure that something in. So I gave us a starting point here. There's lots of different ways you can define variables, but let's use y as the height of the flag in meters, as in height above the ground. I could also say that it's the height, how far it is from the top of the flagpole. I could say how high it is above the soldier's head. So when you're defining variables, you need to have a reference point, like where do I start measuring this from? Time, you usually get to kind of pick it. This one, let's say that y is this height of the flag, as in above the ground, or above the bottom of the flagpole. What about a definition for x in this case? What would the other quantity measured be in this case? Something about time. I hear lots of time. What about time? Okay, time from when the soldier started lowering the flag. And what else do we need in that? In seconds, yeah. So we need to figure out that we're measuring something about the quantity of time, what units we're measuring that time in, and how we start our measurement, what it's relative to. So if we have a number of seconds since the flag left the top of the flagpole, or time in seconds since the flag left the top of the flagpole, again, there's lots of ways, there's not one set of words that's the only ones that work, but we do need to have the units and what we're relative to. So since the flag left the top, so whenever that was, as opposed to time since noon, time since class started, something like that. We might be sensible to say, okay, since the flag left the top of the flagpole. So y was given dx. Here's a way we could say this, and this might not be the words that you chose, but I wanted to show this. A variation in elapsed time, measured in seconds. So since okay, variation in elapsed time. So isn't elapsed time always well, it could be since the beginning, or just some sort of a second went by, or 0.23 seconds went by, or 4.8 seconds went by. So any small amount of time during the lowering of the flag process can go by. We can talk about how long this takes. It'll probably take a while, assuming that the flagpole is not just a couple meters tall. We're going to have dx can be a variety of values. We'll think about small values, but that dx would have to do with changes in or variations in the value of x. So once you've defined your basic variables, your x and your y, your two that are related by that constant rate, you can talk about precisely defining those changes in whatever words make most sense to you. But again, we need to have the units. But notice what dx doesn't have. It doesn't say elapsed time since the flag left the top of the flagpole, because it doesn't have to start at the beginning. We can talk about any little increment of time during the period while the flag is being lowered. So it could be between 4 seconds and 5 seconds after the flag left the top of the flagpole. any sort of increment we want to talk about. So it doesn't have to do with since it left the top. It's just time in seconds went by a little bit during this flag ceremony. So what about dy then? Yeah, variation in the height of the flag during some seconds. But yeah, we'd measured in meters in order to not have to do unit conversions with our constant rate. But what is our constant rate that we'd want to write for a value of the non-variable, a value of this parameter m here? Negative 0.75, right? So we've got a rate where over that rate, one quantity is decreasing as the other increases. So the larger amount of time has passed, the lower the flag's height becomes. So yeah, we want to talk about m. It's that constant rate of change of y to x or y with respect to x. But its value should be something negative here based on how we defined our variables. Because I want the amount of time gone by times negative 0.75 to tell me how much my height has changed. And if I came up with a positive height change, that sounds like the flag's going up. So I want, as time goes by, I want a negative height change, a negative dy value. So I must take my seconds going by, if I'm counting those as positive, times something negative to get a negative result. All right, one more of these. So thinking about this situation, if I ask the question, how much does the height vary between 4 seconds and 6.9 seconds since the flag left the top of the pole? So thinking about our changes, dx, dy, and m. Yeah.
So 6.9 minus 4 times minus 7.
All right, so yeah, 6.9 minus 4, what are you computing when you do 6.9 minus 4 in terms of these symbols? Dx, it's the amount of time that's gone by. In the previous examples, we were told how much the change was. In this example, we have where's the starting and where's the final value of time, which time was our x variable based on previous definitions. So, and this is going to jump out again, I'm sure. But yeah, so our dx would be this variation in time, as we said. So we have, if you want to think of symbols, we could say x final minus x initial. Because lots of times you'll see information given in this way, like, oh, but these numbers are nice enough, so you can say that's 2.9 seconds. But it's 6.9 minus 4 seconds have gone by. So 2.9 measured in seconds. So that's 2.9 seconds elapsed that we're looking at what happens during this 2.9 second interval of time. Does it matter whether it was really between 4 and 6.9 or 5 and 7.9? Now, in terms of the height change, no, it's going to be the same amount of height change. It's the same amount of elapsed time, and we're lowering the flag at a constant rate. So the height change will be the same. Now, the overall height by the end of that is going to be different based on what interval of time we're looking at. But because it's been 2.9 seconds, I know the flag is lowered by one specific amount. And how would I calculate that specific amount again?
Multiply by negative.
Yeah, multiply by negative. What was the number from the previous page? Yeah, it says m dx, and we had negative 0.75. So we'll do 2.9 times negative 0.75, or if you want to write it in the other order, this is our m dx calculation. In other words, I don't have to have y final minus y initial to calculate dy. All I have to have is m dx. If I know the x, the variation in the x, I can find the variation in the y because it's a constant multiple of that. It's negative 0.75 times that because of this relationship. If I didn't know there was a constant rate of change relationship, in order to find the height, I'd have to know the change in height. I'd have to know the starting height and the final height. We don't here, though. It doesn't matter what increment of time we're talking about, where these 2.9 seconds lie in the scope of this flag ceremony. The result from this, which is, I don't know, 2.1-ish or something? I don't know. Negative 2.175? All right. So this negative 2.175 meters, meaning the height decreased by 2.175 meters during this 2.9 second interval of time, or during any 2.9 second interval of time, this one's just a specific example of that, but during any increment of the same length, the flag's height would lower by the same amount. I don't know what the height is. We don't have enough information for that, but we know this information. So m, again, negative 0.75, and it's measured in meters per second. But let's see, I'm gonna clear that off of there. Got one other thing, one other thing I wanna show you for today. I'm just gonna clear this off. And just really quickly, definitions. So we've only got a couple minutes, but just some definitions to think about. This is gonna be part of your, some of you might have read this already, but I think I mentioned as if you wanna get ahead, look at this. But variables, parameters, and constants. I've used those 3 words already earlier today, so I just wanted to, before we leave in a couple minutes, 5 minutes, take a minute to think about what these mean. You're going to read in the textbook more about what they mean and how we use them. But just to be specific, a variable is a letter or a notation. It could be, some sort of, something other than, it could be a set of symbols together. But it's a letter or notation that takes on a value that varies. So in order to be a variable, you have to have something that varies. To point out a common sort of misconstrued definition of variable, lots of times is coming from, like when you first start algebra, when you first start using letter symbols, lots of times say, anytime you see a letter, you call it a variable. Well, some letters aren't variables. Some letters aren't representing things that change, like the M in our previous examples. We used a different value of M in each problem, but that wasn't something that was changing. As time went by, the rate of the flag lowering wasn't changing. It was the same negative 0.75 meters per second. Or the more snack mix you put in your box, the $2 and whatever it was, that didn't change. So that M was not a variable. So things that are variables, you can think of, they generally have a domain associated with them. You can say, oh, it ranges from one point to another, or maybe it can take on any value. So if you can't think of a domain, you're like, well, it's just whatever number it says it is in the problem. Then what you have is not a variable. What you have is something else. So the domain is all the possible values of a variable. Hold on, we still got a few minutes. All the possible values of a variable. Or in context, all the ones that make sense. So if I say, time since the beginning of time, then I wouldn't have negative values for my variable representing time, maybe t. But in any case, there's 2 parts to this. It has to be measuring something that's changing, but it also has to be an actual, like a letter or a symbol. So I can have a concept in my head that's varying, but until I assign a letter or a symbol to it, I don't get to call a concept a variable. I call the variable is the letter itself, but that letter represents this changing quantity. So parameter is the other word I used a few times today. Parameter, in the previous problems, was this M that we had, this constant rate that in one problem was one value and another was another. We're using a symbol, a letter again, and typically it is just a single letter, Greek letter, American letter, whatever kind of alphabet worth of letter you want to use, but it typically is just one, not something like f of x. But it's a single letter typically, where the value stays constant within a given situation. So with our flag problem, it was negative 0.75 the whole time. Now maybe the next day's ceremony, somebody else was doing it and it was a slightly different rate of lowering the flag. But within one situation, something that we're calling a parameter is going to have one value, whether we know it or not, throughout that situation. And so, for instance, I could talk about, what's easy in here? I could talk about this thermos, and I could be filling up water into this thermos, or water bottle. And I could talk about the volume being based on, the volume of water in it being based on how high the water is, which is varying, and what the radius of this is, which is not varying. If I wanted to actually compute the volume of water, I need to know that radius. But if I want to express it, I could just maybe use a letter r. But that r is a parameter if his water bottle is not changing dimensions on us, which is kind of normal. So you can use symbols to represent quantities whose values you don't know. Maybe you'll figure them out later. But if it's something that isn't going to be changing, then we call that a parameter. Now the word constant is reserved for things like pi, or sometimes they're symbol related, like square root of 5, or 17, things that are constants that have one particular value all the time for everybody. So C is a symbol that's used for the speed of light in a vacuum. It is a number that, whatever you know, you may or may not know it, but it is one number for everybody, whether or not you know what it is. So that symbol C, representing a speed of light, as in E equals mc squared, it's a constant. Square root of 3 is a constant. Sometimes they're like symbols, like radical signs. Lots of times, like pi represents the ratio between the circumference and diameter of a circle. It's one specific number. Irrational E, Euler's constant. But things like those are constants. If it's got one value all the time in all situations, and everybody, well, not everybody knows what it is, but everybody could look up what it means, that makes it a constant. If it's something that is constant but it's particular to a problem, and in another problem you could use it as something else, then that's what's called a parameter. But if something is a value that can change, and it doesn't have to be over time, but as one thing, you know, we can make it change in size, change in like an amount of time that goes by, the height of something if that's changing. If we're using a symbol for that, that's a variable. If we're using a symbol for something that's not changing, that's a parameter. And if we're using a symbol to represent a known number, that's a constant. All right, so that is that for today. There is, so that you are aware of this prior to my getting a chance to post the homework assignment, there is a quiz that opened up about 20 seconds ago. It's a 10-minute quiz. You can do it at any time before midnight tonight. 2 questions. I will see you Friday.